In this video, I'm going to discuss the weak field and strong field Zeeman effects. And so the Zeeman effect is something that happens when you put your atom into a magnetic field. And so in a uniform external magnetic field, which we'll call B sub ext, the energy levels are perturbed by this. And so this is our Hamiltonian, the perturbation Hamiltonian in this case. And so we have this mu L and this mu S, which have to do with the magnetic dipole moment of orbital motion and of the spin. And so we will end up with these two terms here. And so when we put that into the Hamiltonian, we end up with this right here, where we have our G sub L and G sub S here, which are our gyromagnetic ratios for these. Then this E, which is the charge of the electron times the h bar Planck's constant over mc and 2mc. So we can put this, so this should actually have a, well, no, that doesn't have a 2 yet, because this GS here is the gyromagnetic ratio, and that is about 2 for the spin there. All right, so in weak field, what we're looking at is when the exterior magnetic field is less strong than the interior magnetic field, where the interior magnetic field is the actual magnetic field of the atom. And so for this, we have that the unperturbed Hamiltonian here plus the Hamiltonian of the fine splitting. We use that as sort of the quote-unquote unperturbed Hamiltonian. And then the H sub Z is the perturbation. And we'll see that this is actually sort of the opposite with the strong field Zeeman effect. But for the weak field, we have this whole thing here, the Hamiltonian plus the Hamiltonian for the fine splitting as the unperturbed Hamiltonian. And then we add the Hamiltonian for the Zeeman effect here as the perturbation. So we end up with the first order perturbation energy as being this, which is what we had from above. Then what I have here in this sort of gold color, we end up just substituting for this mu sub b, which is actually the Bohr magneton. So like I said, the G sub L and the G sub S are the gyromagnetic ratios, of which the G sub L is 1. The G sub S is approximately equal to 2. So if you're into sort of popular science, you may have heard of this this G factor here, which has been sort of measured to, I don't know, something like 12 decimal places or something like that. And so it's not exactly 2, but it is approximately 2. It's 2.00 something. But anyway, in a weak magnetic field, the angular momentum L and the spin S are not individually conserved, but J equals L plus S, which is the total angular momentum, is. And so J is constant, so the L and S precess rapidly around a fixed vector J. And so for both the S, we have the S average and the L average. And so we substitute those back into our Hamiltonian here, and we end up with this the sort of component of L in the J direction, the component of S in the J direction. So that actually looks kind of like this. So we have our L, and then we have our S, and so those are precessing about J, and so it forms this circle here. And so this is from the hyperphysics on the Zeeman effect here. And so we see that we have the L, the S here, they're precessing about J, while J is precessing about the direction of the magnetic field. And so that's in the weak external magnetic field. And what we'll actually see is that in the strong field Zeeman effect, where we have a strong Z, the orbital and spin angular momenta independently precess about the magnetic field direction. And we'll actually see here in a little bit that what's happening is that it's breaking the spin-orbit coupling when we have a magnetic field sufficiently strong enough. But we'll get to that here in a little bit. All right, so we have our J equals L plus S, and so we can set L equal to J minus S and S equal to J minus L. I put these two things side by side here, so we end up with our J dot S and our J dot L. And so the thing to notice here is that the signs are switching. So we have plus S squared minus L squared minus S squared plus L squared. So I do have a lot of the sort of calculations here, or the sort of algebraic manipulations, which I'm not going to go through in painful detail here, but what we do have, we have the average here, which remember is our projection here onto J, and then our projection here onto J for S. And so our J equals this G sub L, L plus G sub S, S. And what we end up with when we make these substitutions up here for the J dot S into the numerator here, and then this J dot L into the numerator there, what we end up with is this right here. And so we use from above the substitutions here. And so I've kind of color coded a few things that we can keep track of. So this half, which comes from the 2 here, the 2 here. And so we end up with this right here. Then we use this substitution here, which is just the eigenvalue for this, for our J squared plus S squared minus L squared and minus S squared plus L squared. And so we end up with this after canceling out this H bar squared, since we see that we have the H bar squared there, and we end up with H bar squared down here in the denominator, so those will just cancel out. Then using that our G sub L is equal to 1 and our G sub S is approximately equal to 2, we substitute those in for our G sub S and G sub L. And so I put this in purple so that we can see where those 2's end up here from the G sub S. We do some more algebraic manipulations, and what we end up with, we end up with this right here, and we call that this G sub J right here. And so we put that in for this. Our J sub Z here is equal to the H bar MJ, so we put that in. This H bar and this H bar cancel, so we end up with this right here. So this is our Zeeman effect perturbation energy, or first order energy for the perturbation. And so the M sub J is able to be a positive or negative, and as I said, this mu sub B is our Bohr magneton. And so when we actually sort of calculate this out, we end up with this 5.788 times 10 to the negative 5 electron volts per Tesla here, or we can put that in terms of joules. So we end up with this 9.273 times 10 to the negative 24 joules per Tesla. All right, since the quantum number m sub L is rotationally invariant, it has an energy degeneracy. But when we add this external magnetic field, that degeneracy is actually broken. So that's why you end up seeing this this split in the lines, which we'll kind of look at here in a little bit. And so, for instance, we have the ground state energy of the Bohr model. So that's the minus 13.6 electron volts, which we've seen from previous videos. So when we look for n equals 1, L equals 0, and J equals 1/2, so we end up with this right here. So we end up with this as our energy for the Bohr plus the fine splitting plus our Zeeman effect. So this term right here is the Bohr plus the fine splitting, and then we have this from our Zeeman effect, where we see we get this plus minus here from the fact that the m sub j can be plus or minus. And so what we see like I said, is that we end up with this splitting here where the plus term splits upward into greater energy, and the minus term here splits downward into lower energy. And so what we actually end up seeing here, so we have without a magnetic field, we have just this single change in energy level here, where when we add this magnetic field, this energy level up here splits into two different ones. This energy level here splits into two different ones, and so we end up seeing multiple lines from this in the weak field Zeeman effect. So you can end up seeing quite a few different lines. But as we'll see for the strong Zeeman effect, which is also sometimes called the Paschen-Back effect, and sorry if I'm mispronouncing that, I've only ever seen this written, but this is sometimes, as I said, called the Paschen-Back effect, but it's oftentimes also called the strong field Zeeman effect. And so in this case, the coupling of the angular momentum and spin is broken, which means that the magnetic field is stronger than the spin-orbit coupling. And so in this case, we instead use this Hz Hamiltonian as the perturbation. Instead of this being the perturbation to the fine splitting, we have the fine splitting as the perturbation to this. And so we have this same thing from above, but now we still have this L plus 2s, with the unperturbed Hamiltonian being this, being the H sub naught, which is our actual unperturbed. But then we're saying that this is sort of the quote-unquote unperturbed, adding the Zeeman effect here. So this is our quote-unquote unperturbed energy right here. And so we have the m sub L and 2m sub S as our eigenvalues. So we still have a degeneracy when m sub L plus 2m sub S is for equal ones of those, such that when m sub L equals 0 and m sub S equals a half, so in this instance we would have L equals 0 and 1. So essentially what I'm saying is there is a degeneracy in L, but no longer in the m sub L and m sub S, which are magnetic and spin quantum numbers. All right, so with the selection rules for the electric dipole transitions, we could ignore the spin degree of freedom. So this is equal to 0, and so we have the change in L equals plus or minus 1, and then the change in ML equals 0 or plus and minus 1. And so since we're still degenerate in L, then at n equals 2, we end up with only 3 spectral lines, which is the m sub L being minus 1, 0, and plus 1. And so that's something that you see with the strong Zeeman effect, is that you end up with just the 3 spectral lines. And so we can look at this example here. So we can, if we have a magnetic field of strength 2.0 teslas, so this is a pretty strong magnetic field. So on this transition here, we have L equals 0 and M sub L equals 0, but for the 1p, we have L equals, this should actually be L equals 1, so I'll change that. So m sub L is equal to negative 1, 0, and plus 1. So we'll have 3 lines. And then our G sub J, remember we ended up finding that being equal to this right here, and so that will just end up being 1. So the energy levels will be separated by this amount. So if we actually calculate it, so we have this as our energy levels here, so the perturbation to our energy level. And so we can have m sub L be minus 1. We put this in, so remember this is the Bohr magneton in terms of joules per Tesla. And then we have 2 Tesla here, which is our external magnetic field. And so we end up with negative 1.9 times 10 to the negative 23 joules. We convert that to a wave number and we get minus 0.96 inverse centimeters. Then if we did the same thing where m sub l equals plus 1, we'd just get plus this 0.96 wave numbers here. So we would end up getting something that looks like this. So this on the left is when the magnetic field is equal to 0. Then on the right side here we have a strong magnetic field. And so we have the m sub l plus 1, the m sub l equals 0, and m sub l equal minus 1. And so in this case up here, this separation from m sub l equals 0 to plus 1 would be 0.96 wave numbers, and then this one right here would be minus 0.96 wave numbers. And so those are distributed about this m sub l equals 0 one right here. All right, so kind of summing up what we've found here. So I found this figure, which I kind of liked. This is linked to, and as usual, the lecture notes will be linked to in the description down below if you wanted to look at this in more detail and click on some of these links. But anyway, this is for sodium here. So the typical lines for sodium. So we have our B equals 0, and we end up getting a doublet. So this is the change in energy of the spin-orbit coupling. We see that in the weak magnetic field, we still get this sort of spin-orbit coupling separation here, but then these two lines here are each separated into more lines right here. And so this goes back to what I was saying, how we say that the Hamiltonian, with the addition of the Hamiltonian for the fine structure, is our quote-unquote unperturbed, because we see that we still have this spin-orbit coupling separation here going on, but then we just have this further separation, this further perturbation caused by the Zeeman effect. But then when we get to the strong field Zeeman effect, or the Paschen-Back effect, we sort of lose this this spin-orbit coupling separation going on here, because that is the perturbation now to our Zeeman effect Hamiltonian. And we end up with these three lines that look like this. And then so I have a few more figures in here that kind of show sort of the same thing. So we have the sodium Zeeman effect, and so in a weak field, weak magnetic field, we end up with these multiple lines here. So we have this one down here, which would just be a single line without a magnetic field that's split into these four lines. So these ones here, then these ones up here. Then we have this right here, which has with no magnetic field, we end up with a single spectral line, and then in a weak magnetic field, we see that split. And then similarly for the strong field here. So what we actually see here is we have this split into these multiple lines, but some of these, like this going down to here, and then this one going down to here, is actually the same energy difference. And so what we actually see, we get these three lines, but this center one here is actually greater intensity. And so again, these are from the hyperphysics, and you can check that out. You can click these links in my lecture notes if you want to. So once again, this is sort of just looking at the same thing. So we have the Zeeman and the Paschen-Back here. So the Zeeman, we end up with these multiple different lines going on here, but then in the strong field, we end up actually with only three lines, because again, some of these are of equal energy. So going from this top one to this top one is the same as going from this middle one to this bottom one here. So these two blue lines here are of equal energy difference. So we end up with only three lines. So again, we have our M sub L plus 2M sub S, and remember that is sort of the the part of our energy that we saw up here. And so, yeah, that is again just sort of looking at the same thing, the difference between the sort of weak field Zeeman and the strong field Zeeman. And again, kind of looking at, well, this is looking at the strong field Zeeman. And so there's this idea when you're looking at this of the longitudinal Zeeman effect and the transverse Zeeman effect, and that is sort of based on the way that you're looking at it, whether you're sort of looking down the magnetic field lines or across the magnetic field lines. And essentially what that will mean is that the longitudinal, you won't see this center line, but in the transverse, you will see the center line. So you'll see the three different lines where in the longitudinal, you see just the two lines on either side. And if you want to know more about that, again, you can click this link. But anyway, that was everything I wanted to discuss in this video. I think the take-home message is sort of summed up well in this one. This figure right here is a nice take-home message for the difference between the weak and strong field Zeeman effects, and how the Zeeman effect sort of affects the spectral lines that you will see from a substance. And this one is also kind of a nice summary of it, where the weak field we see this small splitting, but you'll end up with all these different lines, where the strong field we get this greater splitting, but we end up with fewer lines. But anyway, I hope you found this video helpful, and I will see you in the next one.